Hello and welcome to Escape Velocity Space News in our nth format of N weeks. If you've noticed that things around here keep changing a little bit in style, in length, in how the camera is set up around me, you are right. There are changes afoot. I'm an old school podcaster. I've been podcasting since before it was cool. And I thought I'd be podcasting for forever, and then video came along. And then I started doing video, always with my camera like this. And then TikTok, and Reels, and Shorts, and all these other let's hold our camera the other way forms of communication came along, and we have learned, because I have learned from my own experience, that tired people looking for one good thing in this world will scroll and scroll and scroll and sometimes pause on the science as they try and find something to lull them off to bed at night or occupy their time. And we want to reach those people with science, because you never know whose life you're going to change with science. So we're trying to figure out how to package our show so that we can give you the full YouTube experience, the full podcast experience. I like podcasting. And then chop things up for the shorter ways of getting out information that we know so many more people are willing to consume. We really appreciate your patience as we rearrange our literal screen over and over and over. I think we have it this time. And in addition to having a new camera spread, we also have plenty of science. In this episode, I'm going to be looking at how there might be leftover pieces of another planet in the core of our planet. That's a thing. And we're also going to be looking at new high-resolution images from the ALMA telescope from JWST and so much more. This is, as I said, Escape Velocity Space News, and I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Okay, I have to admit, the JWST is finding objects so exceedingly weird that my first reaction is to say, I'm gonna wait until that is confirmed by someone else, because how? Case in point. In April, the JWST Advanced Deep Extragalactic Survey released a paper saying they had found galaxies in JWST images that appeared to be shining from when the universe was just a few 100 million years old. We talked about this story, but made it clear future data could move these galaxies a bit closer to us in time. And at least one of these galaxies we now know is actually closer, more normal, what we expected. But others are confirmed to be just that far away. Now another collaboration. The Ultra Deep Near Spec and Near Cam Observations before the Epoch of Reionization Team, or Uncover Team, has looked at another region with the JWST and also found galaxies from when the universe was just a few 100 million years old. Folks, our universe made galaxies faster than any professor or research paper ever led me to anticipate. How this happened, I have no idea, but it is super cool to see. To see objects this far away in time and space researchers had to combine the light gathering power of the JWST with the light magnifying power of massive galaxy clusters. The Uncover team used the Pandora cluster, which is located about 4 billion light years away toward the constellation Sculptor. Now, images by JWST, which were released in February, allowed the team to find 60,000 light sources that might be shining from the early universe. And follow-up observations of the best 700 are currently underway. A new paper in the Astrophysical Journal Letters, led by Binji Wang, uses the gold standard technique of spectroscopy to show 2 of these galaxies are shining from when the universe was just 330 million years old. Ranked as the 2nd and 6th oldest known galaxies, they are also the largest systems so far seen, which admittedly still doesn't make them all that big. One appears to be about 2,000 light years across, which makes it 5,000 times smaller than our Milky Way. But viewed in perspective, it's huge. According to Wang, quote, "Previously discovered galaxies at these distances are point sources. They appear as a dot in our images. But one of ours appears elongated, almost like a peanut, and the other looks like a fluffy ball." End quote. These galaxies also have outsized brightnesses because they are full of massive young stars and star formation. They have remarkably few heavy elements in them, and team member Joel Lija explains, quote, "The first elements were forged in the cores of early stars through the process of fusion. It makes sense that these early galaxies don't have heavy elements like metals because they were some of the first factories to build those heavy elements." End quote. Prior to JWST, astronomers couldn't see this region of space-time in any detail. And we're now learning all the things we assumed would be happening are indeed happening just earlier than we dreamed. Our theories got the big picture right, and over time, scientists will work out the details. And time is perhaps the most important building block in massive galaxies. In November, NORLab released a remarkable image of the galaxy NGC 7727 that was taken with the Gemini South Observatory. Seen in colors similar to what our eyes can see in, this image reveals how 2 merging spiral galaxies can create truly beautiful destruction. The arcs and blue highlights in the image, which we have on our website, are pulled out tails of gas and dust that is in some places forming stars at incredible rates. Remarkably, 23 knots of material found in this mess of gas, dust, and stars appear to be newly formed globular clusters, adding support to the theory that globular clusters form where material is slammed together during mergers. Deep in the heart of these 2 systems is a pair of supermassive black holes, one from each of the original galaxies. Throughout the merger, they've been migrating closer and closer and closer, and now they are just 1,600 light years apart. It's hard to know exactly when this merger started, but we do have a sense of when the most exciting part will come. If our models are correct, in about 250 million years, those 2 supermassive black holes will merge in an almighty release of gravitational waves. With a distance of 90 million light years, this system is far enough away to pose no risk, while near enough to potentially give whatever life is kicking around in a 250 million years one heck of a good view. And before you worry about where we'll be then, I checked. And our solar system, I can't say about us, our solar system, will have completed 1 full orbit around the Milky Way. So we should have unobstructed seating for the show. For now, This is just an image release. When science teams have completed their analysis, we'll bring it to you here on EVSN.tv. Our solar system lives in a nice suburb of the Milky Way. Sitting about 25,000 light years from the galactic center, we're in a good place to view what's happening in the core district, but far enough out that things are less crowded and wild. But we're not so far out that there aren't good building materials. Our solar system really did land in the right location. And isn't it all about location, location, location? A lot of what we know about the core comes from seeing the shocks created by past violent flares and the twinkles of radio emission that pass through the dense crowd of dusty structures. Also able to sometimes pass through this material is infrared light. A new image from the JWST pierces through, mostly, to reveal 500,000 stars in the Sagittarius C region. According to lead observer Samuel Crow, quote, "There's never been any infrared data on this region with the level of resolution and sensitivity we get with Webb. So we are seeing lots of features here for the first time," end quote. For instance, there are weird needle-like lines in cyan in the JWST image, and these come from ionized hydrogen gas doing things we just haven't seen before. But that's why we science, to try and understand new things, and science we shall. After a break, we'll be back to explore planetary formation, including the remodeling job Earth did about 4.5 billion years ago. Stay tuned. Sometimes our place in the universe really messes with our ability to understand the universe. From wanting life to be like Earth life, to wanting alien solar systems to look like our solar system, it turns out our wants can bias how we try to science reality. And this means sometimes our theories are just wrong. Folks, our theories for how solar systems evolve just keep turning out to be flawed. It all started with the solar nebula model, which was put forward in 1755 by Immanuel Kant. A natural philosopher with a strong grounding in science, Kant reasoned that our solar system formed through the collapse of a massive cloud of material that began to spin faster and faster as it condensed and flattened. In the heart of the solar nebula, the sun would form, and in that disk, we'd find planets getting their start. And that part of the theory, the part dating back to 1755, appears to be true. It's what came after it that causes us problems. As telescope technology advanced and our cataloging of the contents of our solar system got more detailed, researchers began to build a picture of planetary formation that had our worlds, the major planets and minor bodies, all forming pretty much where we find them today. Rocky worlds, it was told, would form snuggled up next to their suns, while the gas giants would favor farther regions and the icy bodies would orbit in the great cold beyond. It's a pretty story. It does a great job describing the solar system we live in. But towards the end of the last century, we started noticing some issues. For instance, if everything politely formed in situ, why do we see evidence that from 3.8 to 4.1 billion years ago, the sky was falling in the form of asteroids and comets smashing violently onto the surfaces of world after world? We also saw chemistry that didn't quite seem to line up and other little things that all added up to a whole lot of what are we missing? And then in the 1990s, we started finding planets around other stars. The first discovery of a rocky lump orbiting a left-behind pulsar in a system that had experienced a supernova, that was easy to explain as not something our theories had considered. But the next discovery, a world half the size of Jupiter with an orbit less than 1/10 the size of Mercury's, everyone agreed that gas giants aren't supposed to be in the inner parts of a solar system, and astronomers found themselves trying to figure out how to move planets around to make sense of all these new discoveries. And we did pretty good with a new theory introduced in 2005, the Nice model, developed by a group of planetary scientists meeting in the city of Nice, France. This theory imagined our early solar system as a place where everything was on the move up until the bulk of the leftover bits of solar system formation were cleared out. Essentially, the planets formed in a disk, just like before. But this time, about 35 Earth masses of material was scattered amongst all those worlds' orbits. Orbits that were imagined to be a bit more compact and a lot less permanent. As the leftover material interacted with the planets, especially the gassy worlds that migrated outwards as rocky bodies got thrown inwards, well, those rocky planets, they got beat up, creating the craters we associate with the Great Heavy Bombardment. This all culminated, so the story goes, in Jupiter and Saturn ending up in a resonance and flinging other worlds pretty much all over the place, and the rocks also, everything, everywhere. And the theory is sound until you ask, but why didn't the planets fling rocks both inward and outward? Models done by the likes of Kevin Grazier show Jupiter is an equal opportunity flinger of rocks. The theory also breaks down when you look at some of the data of the last 10 years. Since 51 Peg B was discovered in 1995, we have found more than 5,000 worlds orbiting other stars in myriad configurations, thanks to missions like Kepler and TESS. We've also been able to capture images of solar systems in a variety of different stages of formation using systems like the Atacama Large Millimeter and Submillimeter Array and the Very Large Telescope in Chile, as well as the Hubble Space Telescope. The combined reality of all these systems shows us that planets can and will form just about anywhere. And we somehow have to figure out how that happened. We find systems with massive disks. We find systems where stars rapidly blast away their disks. We find just about everything, except a twin to Earth and planets between 1.5 and 2 Earth masses. Can I tell you why? No, I can't. It is now looking like planets can migrate in or out, and planetary formation has to happen faster than previously thought to allow massive worlds to form before their stars blow away all the gases that build those planets' beautiful atmospheres. And I have to admit, I find a lot of comfort in knowing that the formation of a solar system isn't so simple that Kant figured it all out in 1755. Solar systems are the places where we expect life to evolve. And I want that Star Trek universe of myriad life forms that have each found a way to be happy on their own strange new worlds. While our big picture on planet formation still has problems, one good thing we learned is worlds will go smash. Like, we see what appears to be debris clouds in other star systems of worlds that went smash with almighty debris-making force. And this is important because it means we actually do understand where our moon came from. The moon has been observed to be slowly moving away from Earth since the 1960s. This observation gave strength to a 1946 theory from Reginald Daly that the moon was created during a massive impact. Further work by Bill Hartman and Don Davis showed how this kind of an event could lead to an Earth and moon with different densities that reflected a massive collision and a splattering of debris. Researchers who compared Apollo moon samples with this theory's predictions ended up agreeing. A great impact between some Mars-sized world, posthumously named Theia, and a younger and smaller Earth seems to have produced the modern, denser Earth and our shiny moon. But this raises the question, did all the splashy bits really become the moon? Could there be meteors and tiny asteroids all over that were formed in that impact? In a moment of what I thought could be cleverness, I even wondered if rubble pile asteroids could form in this kind of an event. They can't, by the way. I checked. After decades of looking at the chemical composition of all sorts of meteorites, it appears the moon-forming impact didn't fling debris everywhere, at least not debris that later returned. But while meteorite researchers were failing to find pieces of Theia that had fallen back out of the sky, earthquake researchers were finding continent-sized pieces hiding out inside our planet. Turns out, there are two roughly moon-sized chunks of material hanging out at the core mantle boundary inside our planet. One is beneath the continent of Africa, while the other is beneath the Pacific Ocean. These regions have a different density than other material at this depth, and they alter seismic waves as those waves flow through our planet. Discovered in the 1980s, these blobs perplexed researchers for 40 years. Then one day, geophysics student Quan Yan heard planetary scientist Mikhail Zolotov discussing the giant impact hypothesis. And according to Juan, quote, right after Mikhail had said that no one knows where the impactor is now, I had a eureka moment and realized that the iron-rich impactor could have transformed into mantle blobs, end quote. Jan did the work, ran the simulations, and demonstrated for the first time, because computers were finally good enough to demonstrate it, that it's possible for chunks of an impactor to survive inside our world. This is your friendly reminder. Astronomy advances at the pace of technology, one creative individual at a time. The idea of worlds in collision is perhaps as old as the concept of worlds. If you want to imagine a romp through the solar system on a fragment of a disrupted planet Earth, you need go no further than Project Gutenberg. Available for free, Jules Verne's Off on a Comet offers a 1877 imagining of what could happen if a chunk of our world were knocked free. This story does suffer from the social norms of France in the 1870s, but the science is surprisingly well thought out. While still under copyright, Immanuel Velikovsky's 1950 book, Worlds in Collision, is easy to find in the used book market. Written as a scientific treatise, this book is better seen as a creative work. Velikovsky summarizes, quote, Worlds in Collision is a book of wars in the celestial sphere that took place in historical times. In these wars, the planet Earth participated too. The historical cosmological story of this book is based in the evidence of historical texts of many people around the globe, on classical literature, on epics of the northern races, on sacred books of the peoples of the Orient and Occident, on traditions and folklore of primitive peoples, on old astronomical inscriptions and charts, on archaeological finds, and also on geological and paleontological material, end quote. If you want to imagine our solar system at its wildest and most impossible, catch this historic fiction and know, while these authors got things wrong, we still don't actually have all the answers. And again, that's why we're going to keep doing science. After the break, we'll be back with a tech update and news from the Launchpad. As much as some machine learning algorithms would like you to think we can just click enhance, 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 and reveal the real details in otherwise blurry images, we can't. That software is just guessing at what should be in those pixels based on the thousands and millions of images it's been trained on, usually without permission of the image takers. Anyways, when we're looking at objects on the other side of the universe, or even the other side of the solar system, we want to do better than guessing at what might be in our blurry pixels. We want better data, sharper images, and every color of the spectrum. And because our wants are mighty, we build mighty telescopes and then keep refining them as technology advances. And one of my favorite facilities, the Atacama Large Submillimeter and Millimeter Array, has just gotten some pretty cool upgrades that improve its resolution by a factor of 15. That's like going from a 100 pixel image to a 1500 pixel image. This remarkable improvement is thanks to a new calibration technique that is used while observations are being made. Essentially, in this calibration method, a calibration source in longer wavelengths is observed while the science source is observed in shorter wavelengths. Atmospheric fluctuations seen in the calibration source can then be compensated for in the science source. This technique is called band-to-band calibration, and it's already allowing researchers to get a clearer picture on how the star R Leporis is dying. I guess you can say this technique is breathing new life into stellar death. You can say it, but maybe you shouldn't. Anyways. Next up, I'm pleased to welcome on aerospace correspondent Erik Mattis with this week's Tales from the Launchpad. Hey, Erik.
Apart from a launch by the Democratic People's Republic of Korea, this was a pretty light week after all of last week's Starship excitement. We only had 3 Starlink launches, a classified Russian launch, and the launch of internet satellites for the Chinese government. The North Korean launch happened on November 21st and was their 3rd orbital launch attempt of the year. Unlike the first 2 attempts, this one succeeded. The rocket used a modified ICBM first stage and a purpose-built second and third stages. The satellite it put into orbit is called Malangong-1, which means Telescope 1 in Korean. After separation, the first stage exploded. Although no explanation was given, some have speculated this was in order to prevent South Korea, the US, and others from recovering it to analyze its technical capabilities. The rocket's third stage and the satellite have been tracked in orbit by the US military, but no transmissions from the satellite have been detected by amateur observers in North America and Europe. However, it is possible that the satellite only transmits while it's over North Korea. We keep track of orbital launches by launch site, also called spaceport. According to Rocket Launch Live, so far this year, the USA has had 98 launches, China 54, India and Russia each have had 8, Kazakhstan 7, New Zealand 6, French Guiana, Japan, and North Korea each have had 3, and Iran, Israel, South Korea, and the United Kingdom each have had 1. Of these 188 launches, there have been 8 failures, reminding us that space is hard.
As you may remember from last week, I've been just a little bit eager to see if a new volcano will spring forth out of the dark plains of Iceland. At the time of this recording, it hasn't. It actually looks like that super exciting and destructive magma intrusion is now just going to cool off into rock. It could still go off, but every day it doesn't makes it look more and more like this was not the magma intrusion I was hoping for. That doesn't mean some amazing new science didn't still come out of the event. Researchers took advantage of Iceland's thousands and thousands of quakes to refine using fiber optic cables to do geology. It turns out the same cables that carry internet and phone from continent to island can also send back information on what that fiber is experiencing, including data on earthquakes and tsunamis. The smallest deformations in a fiber optic cable can and will cause signal noise. Until now, active noise cancellation was used on the light signal in much the same way my headphones will cancel audio noise. Since each noise reflects something physically happening, it's possible to reverse engineer from the noise signal to the physical incident, like the cable shaking under the influence of a volcano that refuses to erupt. Now, very literally, one person's noise has become someone else's super useful signal. And that's it for now. Good night, everyone, and remember, go outside and look up.